having chosen to attack the problem that we are considering, that is designing of a duct, and under the assumptions that we need to consider, we have defined them. So we have defined the problem in a way, and now we look for its solution. So when we look for the solution, since the velocity u, the axial velocity, is supposed to be, need to keep it linearly increasing, therefore we simply say that u is equal to u1 plus cx. So you can see that it is linear in x and u1 is its initial value. And for cu, we consider it's a constant, and we consider the difference between the end velocity and the velocity at point 2 minus the velocity at u1 divided by delta x. So in that distance delta x, which I think here is about 200 meters, and the velocity is changing from 300 meters per second to 100 meters per second, we take out its original value, and so it's divided by 2 meters, which is the width. So it turns out to be, Cu turns out to be 100 units per second. And rho similarly is also decreasing linearly from one value to another, that are given from 1.2 kilogram to 0.85 kilogram. And when we calculate these values, rho has to be taken, it is assumed to be rho 1 plus C rho over x. And similarly, when we calculate the constant for rho C rho, we obtain its value to be this one. We try to solve this problem, and we need to keep these values in mind. The steady continuity equation for the two-dimensional motion, of course, we have to reduce because it is only a two-dimensional motion, so the variation with respect to the z component, w of the velocity, will be 0, and we will be left with only x and y components, that are u and v. And that is why the continuity equation is reduced to this, and this term is eliminated because it's a two-dimensional motion. Then we try to work out these values. d rho of v by dy, we substitute here the values that we have just obtained. We write it down, and then this value turns out to be, because as you can see they are partial derivatives, we have to integrate them. So when we integrate, we get the value of rho v to be equal to these functions. These are rather constants, times y here, some constant time xy, and here is a constant of integration that we consider possibly can be a function of x, because we are seeing a variation with respect to x as far as density rho and the velocity component u is concerned. So this is what we will obtain for the value of v if we have to obtain at the exit point. That is what we need to consider. We also see that since the bottom of the wall is flat and horizontal, v must be equal to 0 at y is equal to 0. So at that place, the velocity is 0 at y equal to 0 for any x. That means all along the duct, all along the bottom line, the velocity will have a 0 value. Then solving for this, we will obtain this value. And this has simply been worked out already. It's only a matter of substituting for the constants and the unknowns that we have obtained before. We look for the second part, where we have to plot the flow and the duct, and we see that we plot several streamlines between x equal to 0 and x equal to 2 meter, that is within the duct. The streamlines starting at x equal to 0 and y equal to 2 meter approximate the top of the wall of the duct. So this is implying that only we are considering the flow field in the duct. You can see that in the beginning where the wind is initiating, and that is why x is 0 here, y is of course about 2 meters. This is maximum. The wind speed initially is high, and that is how it is to be expected. But the variation of duct is reducing, so its exit is narrowing down, and that is why we say that it is converging. The initial entry point is wider, whereas the exit point is narrower. So it's converging this way. And therefore what happens is that the velocity is going to increase, whereas the density is going to decrease. And remember, it has been already assumed that at the bottom wall, the friction is 0. So we were asked to, the question asked to determine the streamlines, the fluid flow or the flow of the air for different values of y, and that has been plotted here in a rough sketch, and you can see this is how the fluid flow or the flow will look like, and plotting of the graph is shown as indicated. The other thing we need to determine is the streamline at certain points, and the predicted height is also to be determined. That is, what will be this height altogether. Remember, this was about 2 meters in the beginning, and they want to know how much it will be at the end. So that can be seen. Now we can verify that the equation that we derive from this equation and the condition for the designing of the duct, they do satisfactorily satisfy the continuity equation. However, this alone does not guarantee that the density and the velocity components will actually follow these equations if the ducts were to be built as designed here. The converging the duct is such that there is a possibility that it is not necessarily these type of equations satisfy the continuity equation. But in this case, in the particular problem that is under consideration, this has been done and they satisfy the equation. The last part, that the predicted height of the duct will be 0.941 meters. Initially it was 2 meters, and finally it will turn out to be this one, and again it is from these 3 initial equations that we determined. And we also observe that the actual flow depends on the pressure drop between section 2. Normally the flow that takes place is due to pressure drop or pressure changes, and therefore a flow takes place, is generated when there is a pressure change in the atmosphere. Only one unique pressure drop can yield the desired flow acceleration. So this acceleration that has been given, that is the velocity u increasing from initial point to the value that it attains at exit, and also linked with it is the density is also going to decrease in a linear manner from initial point to the point at 2. Temperature variations can also affect, but here we have assumed that they are not taking, they will not be affecting too much the general flow situation. So these are restricted conditions, and that is why we should remember that some of these problems are being discussed as special cases. Special cases means we are imposing some conditions, some assumptions on the type of flow that is being considered.